There we go. Okay, so talk to me about this. How would you go about solving this? Oh, before we do that, before we even talk about how we would solve it, this relates back to our discussion from I guess it was last Friday, maybe, when we talked about solving systems graphically, right? I remember it was Thursday or Friday. Using a graphing calculator. Remember what we ended up doing. And you'll get, so like I say, that's a piece of cake. You'll get some practice on that. The goal there is just to be able to use the calculator to get a quick solution. But there are, as you might expect, going to be two parts to this test. One part is going to be graphing calculator. Go for it. Use the graphing calculator, get the answer quickly. The other part is going to be non-graphing calculator. You're going to have to do this analytically or algebraically. Remember, though, when we talked about solving these systems graphically, what does the end result look like? If I'm going to solve this system, what am I expecting to get for an answer? Okay, an x and a y. Very good. And the x and the y graphically represent the intersection of the two lines, right? But we need both an x and a y. I need the values of x and y that are going to satisfy both equations. Not just one, but they have to make both equations work. So now let's begin to talk about algebraically, how do we approach this? Ideas. Yes, ma'am.
Couldn't you try to cancel out the x's, like times that by -2?
You could. Hold that thought. That's an excellent thought. That's how I personally would do it. Is there another method here? We could use elimination or linear combination. Honestly, I always prefer that. But what's the other option in this case?
I put in the slope-intercept for it to be equal to 2. Is that not work?
Okay, you could, but you're going to find there's an easier way to do it. Okay, so
But is that correct?
it would work. It would work. But our goal here is to make this process as simple as possible. And so your thinking about that was exactly dead on. Let's see if we can come up with a process that's going to get us to the answer a little bit easier. What could we do here other than linear combination? Some people are already thinking ahead to linear combination. Yes, Janelle.
I'd say x on one side
Okay.
and substitute it in the other problem.
Perfect. Okay, we could isolate a variable. We could very easily solve for a variable here, and I assume you're thinking about the x on the bottom, right?
Yeah.
Okay, so I want to know then, somebody else here, help me out. Why did she choose that x on the bottom? Why did she choose to isolate that one? Okay, it's so easy to get by itself. And really the main reason, and she may or may not have even recognized this, but the main reason she picked that was because of its coefficient. What's the coefficient of x there? 1. Okay, good.
Wait, what is this?
So this is substitution. This is going to be substitution. So the first thing we look at here is, first of all, is substitution, I guess these are the steps we're going to go through mentally. Is substitution a viable option?
Yeah.
If it is, you still may decide not to use it. But I think a lot of people, generally I think people like to use substitution when it's easy to do.
When wouldn't it be allowed?
We'll look at an example here soon. Hold that thought. So this is a great option because the coefficient of x is 1. It's so easy to get by itself. What are the steps I have to go through to get the x by itself in the bottom equation? Add 5y, done. One step. That's easy to do, right? So if we solve for x, we get the equation x by itself on one side of the equation equals 5y plus 9, or 9 plus 5y, doesn't matter, right? Okay, that's our substitution equation. So that's a lot of writing for something so simple and obvious, but I'm gonna do it anyway because I'm gonna make an important point about this later. Substitution equation. What I always want you to do, and you're gonna think, this is a great idea because you'll come back to this all year long and forever when you're doing math. When you are using substitution to solve a system, whether it's linear or something much more complicated, when you isolate the variable and solve for it, always, always, always put a box around it. Because you're going to come back to that. That's going to be something you've already done. You're going to come back and rely on that step right there. What you just wrote down is going to save you work later on. You're going to come back to it and use it again. So the substitution equation, box it. Okay, what's next in this process? Plug it in. Good. So the substitution then in a nutshell says we're going to isolate a variable in one equation and substitute it into the other equation. It's got to be the other one, right? We've got to use both equations in the process. So then this x is gonna go in right there, right? Now watch what happens if we do that. The bottom equation, or that top equation then becomes 2 times, but instead of an x, we're plugging in that, right? So we're plugging in 5y plus 9, so that's what used to be an x. And then we'll just continue on. We had plus 3y equals 5. Okay, now at first glance, you might look at that and say, well, why did I do that? That looks a lot worse. That first equation used to look a lot easier. Now there's more term, more numbers. It looks harder, but there's one huge advantage that makes it totally worth it, and what is that? One variable. Okay, good. One variable. We're going to come back to this also again and again, but this is a rule of thumb that I want you to become really familiar with. I want you to be thinking about this stuff. You kind of got to divide your brain up in math. You got to think about things strategically and theoretically on in one part, and then you got to be good, practically speaking, just get the job done and do the algebra. You guys are naturally awesome at the algebra part. You're smart, you're analytical, you can do the algebra without a problem. The part that we always want to kind of work on now is the problem-solving theoretical part, thinking about this kind of big picture, how do I strategically solve these things? Whenever you are solving systems of equations, let's say we're solving a system with 2 variables in it. Here's the rule. You have to have at least as many different equations. We say unique equations in math, but it just means different. At least as many different equations as you have variables to solve for those variables. So if I've got 2 variables, x and y, I have to have 2 equations to solve for those. And I'm sure that kind of makes sense. Look what happened up here when we just took one equation by itself and we solved for x. Well, we got y's in our answer. That's not where we want to end up, right? Our goal is to get numbers for x and y that satisfy both of those equations, right? And so I have to have at least as many equations as I have variables or unknowns. If I have just a single variable, one equation is all I need, right? So what have we done here? By making this substitution, you see that we've done something kind of valuable. We have compressed this system. Instead of having 2 variables, we've compressed it down to a much simpler system with 1 variable and 1 equation. That's always useful to us. And that applies, if we started off with a system with 9 variables and 9 equations, our goal, and no one would ever anymore probably do that stuff by hand, at least linear systems, but our goal would just be to keep compressing that thing down so I can scrunch it down into fewer equations and fewer variables. And that's the process that we would go through. Yes?
Okay, so I might be jumping ahead a little bit.
Okay, that's all right.
But like when we solve for x, then we plug x back into the other equation.
Okay, other way around. When we solve for y, we'll plug it back in. You're right. That's exactly it. Yeah. So look what we get here then. When we make the substitution, all of a sudden now we've got 1 variable in the equation. You guys are awesome. This is where you shift into algebra mode and you just do your stuff and you're done. Real quick, if we had to summarize the process that we go through here, our thinking, what are we going to do to solve for y? First we distribute the 2, then we add like terms, and then just isolate, right?
Yeah.
Make sense? Okay, so if we go through that process real quickly, if I distribute the 2, I get plus. Okay, now this is probably also going to sound a little bizarre to you when I say things like this, but I want you to not write down so many steps. And that's probably contrary to what you've been told in the past, and that's not to say that what you were told in the past was wrong. But as you get to be better at math, a hugely important goal and strategy and technique and all is to be able to do mental math. In fact, if you look, and this is the truth, if you look at the way your brain works, and there is now, I'm really interested in metacognition and brain research that really looks at the way physiologically the brain works. And I think a lot of what we do in teaching and learning needs to be informed by an understanding of how that thing works literally in your head. And here's what people find. When you actually look, this is just one small piece that applies to this situation here in algebra. When you do like a PET scan and you actually look at a brain functioning and you're able to look by, you're looking at the kind of combination of the heat signature in the brain, where it's warmer, where the blood's flowing. You can see that on really small levels with modern technology. And what you can tell is what parts of the brain are active when you're doing certain things. different parts of the brain are active when you're throwing a football than when you're doing other stuff. And so when you're doing, it turns out that when you do algebra, the very same parts or almost the identical parts are active in your brain that are also active when you do mental math. And so it's really important then to, if you want to get the fringe benefit of becoming better at algebra and better at mental math, I mean, they both help, but they help, it's multiplied, the effect, because they both work on the same parts of the brain. So I'm going to kind of push you a lot of times to not be so, maybe on a test you want to be really exacting in your work and double check your work and all that stuff, but when you're just doing algebra, try to do a lot of it in your head. You'll get good at it. You'll get accurate and good at it if you do that. So real quick here, let's combine some steps. Let's start this ball rolling. Combine some steps, and I want you to write down, get all the y terms on one side and all the variable, or all the constants on the other side. What do you end up with if you do that?
13y.
Okay, so y equals, okay, good. So y equals -1. Am I done?
No.
No, halfway done, right? Actually, probably a lot more than halfway done. But half of my answer is complete. I've got the y solution. I know the value of y, but I need the value of x. Now, why did I put a box around that equation? Because I can just go evaluate now, right? In the process of getting a substitution equation, I isolated x in terms of y. Well, now that I know what y is, look, I just plug that in, right? That's easy. So it's 3, right? Okay, let me get real quick. I want to kind of get, this is a big group, but I want to get some, give me a 1 to 5 on that. Does that process ringing a bell, making sense? 5 meaning perfect, 1 meaning whoa.
5 out of 5.
Okay, okay.
Feels good.
All right.
Can I ask you a question?
Yes.
Okay, so when I
Yeah,
saw
quiet, please, quiet. Listen, this isn't gonna work. I can see you guys are doing good stuff, but we gotta hold the, hold on for just a second. It's a good question, but ask it to everybody here in a second. Maybe this answers it.
okay, like when we plug y back in, does it matter if we use x minus 5y equals 9 or x equals 5 minus 9? Does it matter?
When we, oh, okay, yes. Yes, it does. Do you use this one or this one? Okay, yes, it does. See, this is the point I'm making. That in the process of solving for x, you've already got that x by itself. When I know what y is, when I know what the second variable is, I can plug back into this boxed equation, and I'm just going to get some, when I simplify the y side of that equation, I'm just evaluating that expression for a number.
Okay.
See what I'm saying? Then I've already got x equals. I already know my answer is going to be x equals. The question is just what number am I getting back with it? Okay, and it ends up being 3 this time, right? Is it 3?
No.
4, sorry, 4.
Wait, you can't put it in, you can't put y into like those top two?
I could, but why make that extra step of putting it over here and then having to isolate x when x is already by itself there?
More mental math.
Okay, more mental math. There's the upside. Okay. Does that make sense?
Yes.
Okay, so our answer then, our solution, remember, is now going to be the ordered pair. X equals 4, y equals -1, and graphically, what is that again? If I think of the graph of these lines?
The intersection.
Ah, the intersection. Good, that's the point of intersection. Very good. Okay?
What happens when they're parallel? You're just gonna make us keep doing this?
No, we'll look at that. Good question. Thinking ahead, that's
You
good.
already know it.
Well, you'll see. We'll look at the very end. That's an easy case. That's a good news. That makes things easier. Okay, so moving on. That was a good one because the x was easy to isolate. Take a second and look at this one. That's that 9 is really ugly. I drew that one on my computer with my mouse. It didn't work out real well. Okay, so everybody on your own, stop talking, on your own at first. Look at that. Ask yourself same questions. Is substitution yay or nay? Thumbs up or thumbs down on substitution? And if so, which variable would I isolate?
I say
Nay.
yay.
Okay.
Yay.
Okay. Okay, now if you're saying nay just because you prefer to do elimination, that's okay. But let me rephrase the question. Would substitution be a reasonable option? Okay, it would. It would be reasonable to do because which variable is easy to isolate? Okay, good. Now I'm gonna throw something else at you. this is gonna, this seemingly is a slam dunk. Justin, please. You guys, this is an easy one to do, but I wanna challenge the way you do mental math on this just a little bit. And there's, you might be thinking, why? It's so simple. But you can make this a one-step operation instead of a two-step operation if you think about this differently than the traditional way. I'm gonna isolate the y, agreed?
Yeah.
Okay, now if we follow the traditional route of getting that y by itself on the left in the bottom equation, what are the steps I have to go through? What do I do first?
Subtraction.
Okay, I'm gonna subtract 2x from both sides first, right? So I'd go, first step would get me negative y equals negative 2x plus 3. Second step would be what? Okay, divide by -1. Same thing as multiplying by -1. Those are always interchangeable. And what's the effect of that if I take a linear equation and I multiply both sides by -1? Yeah, I'm just trading signs, right? All the signs are going to become the opposites. So we just end up with a positive y equals 2x minus 3. Nothing too difficult about that. We got to our spot. But people that are really good at algebra begin to see this. It's almost like in programming when you do object-oriented programming. When you think about things in terms of almost like a cartoon or a movie. Think about things visually instead of just always being analytical about it. Solving equations is much that way. What you're really doing, if you can think about it this way, and I think even though it might sound weird at first, you'll be talking like this soon too, and it really makes things easier. We're really just pushing terms around that equal sign. The equal sign is staying put, and I'm going to kind of push pieces in that equation around in the easiest way I can to get a variable by itself, right? So although I could isolate that y in these two steps, what's another approach to getting the y by itself?
Add lines.
Ah, okay, good. I could just push the y to the other side, couldn't I? By adding y to both sides. The advantage being, then it's positive, right? And so really, in one step, I could push the y over there and the 3 over there, couldn't I?
Yeah.
Agreed?
Yeah.
So if I do that, I end up with, on the left side, I just get 2x minus 3. Agreed?
Yeah.
On the right side, I get a y. And never let the fact that the y is on the wrong side be any issue at all, because it doesn't make any difference. I can write an equation in any order I want to. So I could just put the y on the left if I wanted instead, without even having to make it an algebra step. It's just true in general, right? Does that make sense?
Yeah.
That is a little easier. Okay, either way you slice it though, we've got this y written in terms of x, and so now I could just plug it in and go to town. We won't even do that. That's a piece of cake. You can do that. That's no problem. Okay, now what happens though when you get something like this? Okay, aha, good. Substitution is no longer. Oh, go ahead. You saw something there.
The X's.
Oh, they multiply the top equal to.
Okay, never mind.
Oh, no.
The y
No, yeah, the X's, you could multiply the X, the top one by 2.
Yeah. And then
Okay.
by -2. And then
There's 15.
You're right. Okay, thanks. Okay, so people are seeing lots of stuff going on here, which is good. Let me point out a couple things. First of all, it doesn't really make any difference if these numbers, if the constants on the right side are the same number or opposites. It doesn't make any difference. They could be, and there still could be a single solution. Don't let that pattern creep into your brain, because it doesn't matter. And we'll see an example of that soon. But this is a case where, worst case scenario, it's really ugly to isolate a variable. Best case scenario, it works out, but it still takes too many steps. This is one where you actually could make it work pretty easily, because both of the, 3 divides evenly into -6, right? I could solve this bottom equation for y, and it wouldn't be that big a deal by, adding -6x to both sides, or adding 6x to both sides, sorry, and then dividing by -3. Still takes 2 steps. I would argue if it takes 2 steps, that's 1 step too many. And what if this number hadn't been -6? What if it had been like -5? Then it would have been a real problem to solve for y. Our answer would have involved fractions, right? Okay, right, exactly. And Say it again. Okay, good question, listen please. Clancy asked the question, why can't I have fractions? Are we discriminating against fractions? It could, but would everybody agree here, by show of hands, how many people would prefer to do arithmetic involving integers as opposed to fractions? Okay, I'll raise my hand because I would much prefer to do arithmetic with integers. Okay, and that's why. That's why. No, you're not the bad guy.
You are the bad guy.
Okay. Oh. Thank you. Okay, so we don't really want to use substitution here because we're going to have to wrestle with fractions the whole way through. We want to use linear combination instead. Okay. Now, using linear combination, our goal is, remember, is to, or elimination, is to get one of the variables to cancel when I add the two equations up. Okay? And first of all, is that okay to do? It seems weird adding equations up. It is. I know that if you think about the rules of algebra, it's always okay to do the same arithmetic steps, so adding, subtracting, multiplying, dividing, both sides by the same thing, right? If I treat both sides equally, in a nutshell, this is a kind of a rule of thumb. As long as I treat both sides of an equation equally, that's fair game, right? Yeah. So adding the same thing to both sides should be a fair move, right? Well, if these are equations, isn't the left side equal to the right side? So if I add two equations together, I'm adding the same thing to both sides of the original equation, right? Okay, so that's okay to do. That's not a great idea here, though. If I add these equations up, it doesn't buy me anything because I end up getting x's and y's equal some number. So the new equation I get at this point, if I add these two up, is no better than either of the original two equations. So why do it? But we could manipulate this system a little bit so that adding the two equations would be helpful to us. Now, who's going to suggest what we could do to these two equations? Yes, sir.
You could multiply the first equation by 2.
Okay, multiply the first one by 2. Good. And so here's how I like to show that. There's different ways of showing this, but I also think in algebra it's important to have good notation so you can follow your own work easily. Here's one way to do that. I'm going to use an arrow with a circle in the middle, and if I'm multiplying both sides of an equation by a number, write that number in. Okay?
Really big bug.
Oh, yeah.
It's not a bug.
Okay, so here we go. Big bug, that's bad, but we gotta do math. Here we go. You guys are gonna run the risk of not getting all this stuff, and this is bad, because the last period did. If I multiply the top by 2, just check my work. I gotta kind of go a little faster here. I'm gonna speed this up. I'm just gonna get 6x for the first term, second term 4y, and then the constant is 12. Agreed?
Yeah.
Bottom one we'll just leave alone. Just make a direct arrow over there. We're multiplying by 1. I don't even have to write that. It's remaining unchanged. So I get negative 6x minus 3y equals negative 6. Now the goal of that was, remember, now when I add these two equations together, one of the variables is going to drop out. I'm going to eliminate a variable. That worked. I accomplished the goal because I had opposite sign coefficients. Right? So 6x and minus 6x add to 0. The x's are gone. Okay, now when I add the rest of this stuff up, I'm going to get a y, and I'm going to get a 6. Okay? Now, worst case scenario, and this is going to happen a lot, you're going to get some coefficient of y, but even if you do, it's just a one-step problem to solve for y, right? Yep. Just divide. So this even worked out better. I got my y equals 6. That's half of the problem. Now, what do I do to solve for x?
In the first one.
Okay, I plug it back in. Okay, but here's the question. I plug it back in. Where?
The first one.
Oh, okay, good. Why not, thinking about this logically and strategically, why not plug it into the equations that have the smallest coefficients? Why not plug it into the original equations before I've multiplied by stuff to make the coefficients bigger, right?
Yeah.
And of the first two, pick the one with the smallest coefficients. Top one. Okay, so we'll plug y equals 6 into the top equation. We're going to get 3x plus 2 times 6 equals 6, and we can solve that for x easily. Okay, good. All right, so I'm going to just just in case we don't get through everything here, I'm gonna skip ahead just a tiny bit. Okay, what about this case? Okay, what do I do in a case like that? Okay, no, you're right. There's no single number I can multiply one equation by, but I might have to multiply both. So which variables are we going to try to get rid of here most easily? I want to multiply by the easiest things. Probably okay, x's, that's fine. If I want to get the x's to go away, I got to think of the smallest common multiple of 9 and 12. How about if we, let's say it again?
Could you like divide?
Not really, right? I'm trying to multiply both equations by a number so that I can get the smallest possible values of x or y to cancel. It might even be better to use the y's because 6 and 8 are a little smaller than 9 and 12.
What if you divided the top by a negative 3 and the bottom by 4? And then they're just both little simple things.
Okay, I see what you're saying. So you could multiply through by fractions or divide. You could, and that would work. There's no reason that wouldn't work. You could. I won't stop you. Yeah. Yes, ma'am.
Why can't you set them equal to each other so they have to, they are both equal to 0?
You could, but if I set them equal to each other, then I've got a single equation with both x's and y's in it, and I'm stuck.
Wait, I thought you
See?
were multiply them both by the same on top and bottom.
No, you don't. I can multiply. Sure. Yeah, I can multiply top by a different number than the bottom. My goal is to get one of the two variables to drop out. What about the x's? What's the smallest number that both 6 and 8 go into that you can think of? 24. Okay. So I want to get a positive 24 and a negative 24 then. Let's multiply the top by positive 4, how about? Okay. Nope. Bottom by negative 3. Okay. Okay, what am I going to get on the top if I distribute that all the way through? Okay, back table. What am I going to get if I distribute the 4 all the way through the top? Okay, I'm going to get negative 36x plus 24y equals 0. Okay, bottom one by negative 3.
Whoa, wait, they all have
They're equal to each other.
Whoa, what happened?
It is, it's an infinite.
Okay, so now look what happened. In the process of getting the y's to cancel, and you did that correctly, by the way, it just so happens that the x's canceled also. And so when I do this problem, when I add these things up, negative 36 plus 36 cancels, right? 24 plus negative 24y plus negative 24y cancels. So the whole left side adds to 0.
So that's because like those are all
that-
30s and those are all 20s.
Yeah.
So you wouldn't even have to do that. So you're
If you
trying
get
to
really good at
calculate
this,
each
yeah.
step.
You get really good at it.
So is that parallel or is that?
Okay, good question. So we get an answer. So we get an answer then that's 0 equals 0. That's a true statement without variables. If we get a statement that's always true, how do we interpret that? How many solutions we can get? Infinite. Always true, you can sort of equate in your mind as with being infinitely true. So we get infinite number of solutions. What does that mean in terms of the lines then? Same line, yeah. Okay, so we get infinite solutions here. Now what if in that original equation though, let's just say, I'm going to leave the same numbers because we've already done all the math. What if we had negative 9x plus 6y equals 1 and negative 12x plus 8y equals 0? Okay? I would have done the same stuff, probably to try to get the y's to cancel. Right? So if I multiply by 4 and negative 3, I'm going to get the same answer on the top, but instead of a 0, I'm going to get a what? 4. Okay, so this is going to look like negative 36x plus 24y equals 4. On the bottom, I get positive 36x minus 24y equals 0. Add them up. Everything cancels on the left, so I get a 0. On the right side, I get 4
That's no solution.
Right.
That's no solution, because it's never true,
No.
okay?
But
So
if
those are
you
parallel.
actually
So those are
got
parallel, exactly.
If
Then
you
you-
actually got one that actually like has like one equal something, which solution would you put it into?
You'd put it into either one, it wouldn't make any difference. Yeah.
An original.
Yep. Okay, so we hit the main goals. Last one I want to take a quick look at, being as, there's no sense going down there now anyway, is one like this, like that, okay? So what about this guy here?
3 and 4.
Okay, so 3 and 4 would be the ones, we'd want to get the x's to cancel because they're smaller numbers in this case, right? Top by 4, bottom by -3, okay?
Or top by 8.
Or vice versa, it doesn't make any difference. One's got to be positive and one's got to be negative though, right?
Yeah.
Okay, so that's going to give us 12x minus 20y equals 40. And negative 12x minus 21y equals negative 27. Okay, it worked, right? Okay, when I add these things up though, we got an answer. When I add these things up, the x's go away, and so I get an answer of negative 41y equals positive 13.
That's
Yes, ma'am.
big. Wouldn't it have been harder
Listen, please. Zoe, you got it? Go ahead.
if you multiplied it by -4 and +3, because then you would get 41y.
Oh, yeah, maybe, yeah. It's a good plan. If you can see that far ahead, that's good. I mean, that's absolutely. When I solve this thing, and what that saves you is having to think about dividing by a negative, I guess. When I solve this thing, I'm going to get y equals positive over negative is negative. We pull the negative out front. It's a fraction. That's my point. So that's what we got to kind of figure out how to deal with. Yes. All right. Have a good lunch.